Yeah, so this is about fast algorithms for inference problems. So I'm going to discuss two problems, regression and low-rank approximation. I'll discuss classical versions for these problems, least squares regression and singular value decomposition. And then I'll discuss more robust measures for these problems. And in both cases, I'm going to show how to use compression to compress your data, but still keep it in a useful way so that you can do fast optimization on the compressed versions of these problems. So let me start off with the regression problem. What you're given is an n by d matrix A and an n-dimensional column vector B. Okay, and in regression, think of n as the number of observations of some process, and d is the number of variables. These are called predictor variables. And the goal in regression is very simple. You just want to find a d-dimensional vector x, x star, so that ax star and b are close. Okay, so A is an n by d matrix, and x star is taking linear combinations of its columns, and you get ax star and b, and you want them to be close under some notion of closeness. Throughout the talk, we're going to consider the overconstrained case when n is much larger than d. So this matrix A is a very tall, thin matrix, and there need not exist a solution ax star equals b. Okay. So one of the most well-studied forms of regression is least squares regression. And here you try to find the vector x, which minimizes the Euclidean distance between these two vectors ax and b, okay, or equivalently the square of that. And this has a nice geometric interpretation. Ax star is just the projection of b onto the linear span of the columns of A. And it also has certain desirable statistical properties. Okay, so if ax equals b up to some independent Gaussian noise that's being added on each of the coordinates, then it turns out that if you solve with this loss function, then you get the maximum likelihood estimator for that problem. Moreover, the solution can be written in a closed form. Okay, so this is really nice in the sense that I can just write down x star as A transpose A inverse times A transpose B. This is assuming the columns of A are linearly independent. If they're not, you can write it in terms of the pseudo-inverse. Okay, so this is a classical inference problem. I'm solving regression. The problem is that if I have very large data sets, computing this optimal solution is slow. I have to compute A transpose A. I'm multiplying an n by d matrix by its transpose. This takes nd squared time naively. You can do a bit better with fast matrix multiplication, but we want to do much better than that. Okay, so to improve upon this time complexity, we're going to use the idea of sketching. And first, we're going to relax the problem to allow for outputting an approximate solution x. Okay, what that means is a relative error solution. We'd like to output a d-dimensional vector x prime for which the cost, the distance between ax prime and b, is at most 1 plus epsilon times the optimal least squares regression cost, okay, with some high probability. Okay, so the way we're going to do this is what I call the sketch and solve paradigm. So we're going to choose a random matrix S from a certain family of matrices, and I'll describe those in a minute. One important property about S, though, is it's very wide and fat. Okay, so it has k rows for a very small value of k. Think of it as being independent of n. Maybe k is something like d over epsilon squared. And you should think of, remember, we're in this case where n is much larger than d. Okay, this overconstrained case. We have a tall, thin matrix. So k is very small. And you just choose this matrix S. Then you compute S times A and S times B. Okay? And now all you do is you replace the original matrix A in the regression problem with S times A, and the original vector B with S times B. And now you can just solve this regression problem, this least squares problem, exactly using the formula that I just described. And now it's efficient because I multiply this wide fat matrix S by A, this tall thin matrix, and I squash it to a roughly small square matrix. And I also reduce the dimension of B from N down to K. Okay? So this is the sketch and solve paradigm. So the cost really is, for the regression problem, is computing S times A and S times B. And then solving this exactly is just going to take some polynomial in K and D time, which is, I like to think of as low order, okay, if D is much less than N. Okay, so a natural question is how to choose this sketching matrix S so that this sketch and solve method works. So lots of families of matrices work. The first you might try is a matrix of IID normal random variables. And this actually does work. So if I set the number of rows to be d over epsilon squared in my matrix S, and I do this sketch and solve paradigm, I will get a relative error 1 plus epsilon approximation. But there's a problem with using this matrix S. Does anyone know what the problem is? Yeah, so storing the matrix is, I have this dense matrix, storing it is a problem, but also just computing S times A, right? Because S is very dense. I'm computing S times A. S has even more than D rows, and we said we could already solve the problem exactly just by multiplying A by A transpose in ND squared time. Now we're going to spend even more time, ND squared over epsilon squared time to do this multiplication. So we haven't really gained anything. But in a very nice paper of Sarlos, he observed that instead you can choose S from a much more structured random family of matrices, namely the so-called fast-Johnson-Lindenstrauss transforms. So these have the property that you can compute S times A much faster. Typically they can be factored into the product of three matrices, P, H, and D. And each of these factors can be applied to a vector, an n-dimensional vector, very quickly. So D is just a diagonal matrix, and the entries on the diagonal are independent plus minus 1 entries. Okay, so each is 1 with probability 1/2 and minus 1 with probability 1/2 independently. So I can apply that to an n-dimensional vector in order n time. H is a fixed matrix. It's the Hadamard matrix. So the nice thing about H is it has a fast transform. I can apply it to an n-dimensional vector in n log n time as opposed to n squared for general dense matrices. And P just chooses a random small subset of rows of H times D. Okay, so when I apply it to a vector, it's just sampling a small subset of coordinates, and so that can be applied in even sublinear time. So yeah, the point is S times A can now be computed much faster. For each of the D columns, I can compute S times that column in n log n time, okay, giving overall nd log n time. So whereas using Gaussians gave nd squared. And you can show that this, if I do this sketch and solve with this matrix S, then I will get a relative error solution. I won't prove that, but roughly the intuition is that a minimal property that you need about S is when you apply it to a vector, you preserve its Euclidean norm. And one way of estimating the Euclidean norm of a vector is to sample coordinates. And that's what P is doing. However, if you have a very sparse vector, sampling has very high variance, you'll miss all of the non-zero coordinates. And so the goal of H times D is to spread out the Euclidean mass across all of the coordinates. So this is the intuition. So that gives you nd log n time to compute S times A and S times B. And then now you can solve the small instance of regression in polynomial and D and epsilon at much lower running time. OK, so that's optimal in the matrix dimensions. But what we showed a few years ago is that you can actually get algorithms that depend on the number of non-zero entries of your matrix A. OK, so oftentimes your matrix A is very sparse. It might only have order n non-zero entries, for example, out of n times d. And you'd like running time proportional to that sparsity. So instead, what you can use is what's called a count sketch matrix from the streaming literature. It's again a wide fat matrix with k rows, but now k is a little bit larger. Instead of being d over epsilon squared, it's d squared over epsilon squared. But the nice thing about S is it's extremely sparse. Okay, so here's a picture of S. It just has a single non-zero entry in each column. This entry is chosen in a uniformly random position. And the entry is 1 with probability 1/2 and -1 with probability 1/2. Okay, independent across the columns. And now you can see that S times A is computable in n and z of A, number of non-zero entries of A time. Why? Because for each non-zero entry of A, it corresponds to a column of S, and there's only a single non-zero entry in that column. Okay, so it's much faster. You can also, there's nice work by Meng, Mahoney, Miller, Peng, and Nelson Nguyen, which gives trade-offs here. So if I increase the sparsity, instead of a single non-zero entry per column, if I have a small number of non-zero entries per column, I can reduce this k to being closer to d over epsilon squared. So there are trade-offs there. But importantly here, k does not depend on n. And surprisingly, this actually works. So if you do compute S times A and S times B and solve the problem in the sketch space, your solution will be a relative error solution for the original problem. Okay? So that's what I wanted to say about least squares regression. Any questions about that? Okay. So let me move on to more robust versions of regression and how you can use sketching to speed those up as well. So another notion of closeness for regression is what's called L1 regression. And the only difference is now you find an x which minimizes the L1 distance between AX and B. Okay, the sum of over the n coordinates of the absolute value of BI minus the ith row of A and X. Okay, as opposed to the squared value. And because of that, it's often less sensitive to outliers than least squares. Okay, so if I have one very large value of BI, I'm not trying to fit it as much with my choice of X because I'm not squaring the distance. So maybe I can capture more of the remaining coordinates. So it's more robust in that sense. Again, you can solve this problem exactly, or at least to machine precision, using linear programming. But it's not very efficient. Okay, it's polynomial in n and d time. If n and d are large, you want much faster algorithms. And there are also many other fitness measures used in practice. There's this whole theory of M-estimators. So this is based on defining a function m from the reals to the non-negative reals with some basic nice properties. It's symmetric about the origin. It's 0 at 0. And it's non-decreasing in the absolute value of x. Okay? I define this m function, and now I can define the m norm. It's not a norm, but let me just call it that. So the m norm of a vector y is just the sum of m applied to each of its coordinates. And given that, I can define a regression problem. Okay, so I try to find an x which minimizes the m norm of ax minus b. And you can see that least squares and L1 regression are special cases where m was the square function or the absolute value function. What are other interesting m functions that people use? So one is called the Huber loss function. It has some formula, but just pictorially what's going on is it's quadratic near the origin, just like least squares was. And then at some point it becomes linear. Okay, just like L1 regression was. And it's nice that it's, unlike L1 regression, it's actually differentiable at the origin, which is very useful in optimization procedures. And unlike least squares, it's robust in the sense that as I move away, I'm linear as opposed to quadratic, which is exactly when I want to be linear. And there are many other loss functions that have similar behavior. They're basically quadratic, and at some point they become linear. And this motivates the definition of a nice M-estimator. we say an M function is nice if it has at least linear growth and at most quadratic growth. Formally, there's a constant depending on the choice of M function, so that for all arguments a and a prime, where a is larger than a prime, the growth, the ratio of M of a to M of a prime, is at most quadratic and at least linear, okay, times that constant. It's worth noting that any convex function M satisfies the linear lower bound. And oftentimes you want your M function to be convex, because then you can solve this M regression using general convex programming, because sort of the sum of convex functions is convex, so the whole problem is convex. Though other non-convex functions also satisfy this. And loosely speaking, any sketchable M satisfies this quadratic upper bound. Okay, so what does that mean? So just loosely speaking, sketchable means that there is a distribution on these wide fat matrices S that we used in the sketch and solve paradigm. These wide fat matrices S, for which if I compute the M norm of Sx, it's roughly equal to the M norm of X with good probability. Okay, and you really need the quadratic growth upper bound for this to hold. For instance, if your M function were X cubed, then you wouldn't have such small matrices S. Okay, so in that case, the number of rows would need to be at least n to the 1/3. And we really want to squash the problem down to a problem independent or only polylogarithmic in this large dimension n. Okay, so that's motivation for this. And what our result is that is the following. So in n and z of a plus poly d log n time, we can output a solution x prime, which is a relative error approximation to the M norm regression problem, okay, for any nice M function. So yeah, the cost of our solution is at most c times the cost of the optimal solution, where c is a constant greater than 1. I wrote it like this instead of writing it as 1 plus epsilon, because the dependence on epsilon is pretty bad. For the full class of nice M-estimators, the dependence on epsilon is actually exponential. But you can get an interesting subclass where you get polynomial dependence. But let me just ignore that issue here. Some remarks about this. So as I said, for any convex nice M-estimator, you can solve it in poly ND time. But our running time is much faster, right? It's n and z of a time. Okay, so I have an n by d matrix. N and z of a is at most n times d, which is much faster than this, but it can be as small as order n. Another thing is our sketch is universal in a certain sense, which is that we're going to solve this problem using the sketch and solve paradigm. And what we can do is we can take our instance of regression, we can sketch it down to something small, and the same sketch matrix will work for any nice M-estimator. Okay, so then you can later decide which M function you want to use. Let me just say what the sketch is. So we call it the M sketch. So it has the property that it can be applied to a matrix very quickly. It's a block matrix with log n blocks. The first block, S0, D0. The next one, S1 times D1. Each of the SI's are independent count sketch matrices. Okay, these very sparse matrices with a single non-zero entry per column, with some poly d number of rows. And each of these matrices di is diagonal. Okay, and what it is on the diagonal it has zeros and ones, and it has a roughly, the ith diagonal matrix has a roughly 1 over d log n to the I fraction of ones. Okay, so D0 is the identity matrix. D1 is sampling 1 over d log n fraction of the n coordinates. Okay, those correspond to the ones on the diagonal, and the zeros correspond to the things you don't sample. So you see that the di's SI times di can be applied in number of non-zero entries of a time, for a typical non-zero element, you only go down a constant number of blocks before it's, you only have to process a constant number of blocks. So overall, you get n and z of a time. And after I go down log n levels, d log n is just 0. So there's no reason to go further. I want to mention that, so this M sketch doesn't depend on the function M. And so it works for all nice M estimators. Namely, if we compute t times A and t times B and solve the M-norm regression on that much smaller problem, then we'll get a relative error solution. This sketch is used quite frequently in the data stream literature for estimating frequency moments, for earth mover distance. But I want to mention one thing is that many analyses of this data structure, they don't work in our setting because they reduce the original problem to a non-convex problem. Okay, because they use things like median operations, etc., inside of the sketch space. And here it's really important that we take our regression problem and reduce it to a smaller version of itself. Okay, for instance, if we'll do things like preserve convexity and then have efficient algorithms on the small problem. Okay, so this is all I wanted to say about robust regression. Any questions about that? Yeah. Oh, so this already comes from things like estimating the L1 norm of a vector. If you want, sort of like what's happening in this sketch is you're getting, when I apply this sketch to a vector, it's with very high probability I don't contract the M norm of that vector. But it actually does increase the dilation. I might actually dilate and get a much larger M norm. And sort of controlling that dilation is where the blow up is coming from.
Like the index
exactly. Exactly, yeah. Yeah, for L1, yeah. Yeah, I didn't really give intuition why this is why this works, but note at the top level S0 times D0 is exactly the sketching matrix we use for least squares regression. And what we're doing with these multiple levels is we're trying to estimate the M norm at all scales. Okay, so we're throwing out 1 over d log n fraction of coordinates, then throwing out even more coordinates, etc., and then applying count sketch only on the surviving coordinates. And so we're really trying to capture the M norm at every scale. And this is important because the M norm could behave very differently at different scales. You saw this Huber loss function where it's quadratic near the origin and then it becomes linear. So that's some intuition. Okay, so let me move on to the other problem I wanted to talk about, which is low rank approximation. So in low rank approximation, you're given an n by d matrix A, and think, just like in regression, and think of the n rows as being points in R to the d. For example, A might be a customer product matrix. Aij might indicate how many times customer I purchased item J. Or in image processing, each of these rows of A is an image, and the value is the intensity at a coordinate. Oftentimes, your matrix A is well approximated by a low rank matrix. For instance, it might only be high rank because of noise. And the goal is to find a low rank matrix approximating A. For instance, it's easy to store in factored form. It could make your data more interpretable if it's actually corresponding to removing noise. So the standard way of solving this problem is through the singular value decomposition. So given my matrix A, any matrix A can be written as U times sigma times V, where U has orthonormal columns, sigma is diagonal with non-negative, non-increasing values as they go down the diagonal, and V is orthonormal rows. And so the natural rank K approximation is the truncated SVD. So I take sigma K, I take the top K diagonal elements, and I just zero out everything else. And that corresponds to selecting the K leftmost vectors in U and the K uppermost vectors in V. And that gives me a rank K approximation to A with some error matrix. Okay, whatever is left. And the nice thing about this, and these VK, these rows are known as the top K principal components. The nice thing about this is that A sub k is the best rank k matrix for approximating A under a large number of norms, in particular under the Frobenius norm. Okay, so it's the minimizer over rank k matrices B of the Frobenius norm of A minus B. Okay, where the Frobenius norm is just the sum of squares of the entries, the square root of that. Okay. So the only problem with this is computing A sub k exactly is expensive. Okay, solving an SVD takes nd squared time, or if in this case d might be even larger than n, you can do n squared d time as well. But we want much faster algorithms. Okay, so just like for regression, we're going to use this sketch and solve paradigm to obtain very fast algorithms. We first relax the problem as before to allowing for a relative error solution. We output a rank k matrix A prime, which approximates A as well as the best rank k matrix up to a 1 plus epsilon factor. And what we can show is we can solve this problem in time n and z of A plus a lower order term, typically n plus d times poly k over epsilon. Okay, so you know, the SVD was nd squared time. Even for dense matrices, this is only nd. So let me give you some intuition of how this algorithm works. Okay, so you're given this n by d input matrix A, and think of the n rows of A as being points in R to the d. Then the first step is to choose one of these wide fat matrices S, okay, with a small number of rows. Think of the number of rows as being something like k over epsilon. You compute S times A. Okay, now suppose I look at the span of the rows inside of S times A. That's a k over epsilon dimensional subspace of R to the d. And I've drawn that here as a line. Okay? Then the next step is to take your n points, the rows of A, and project them onto this k over epsilon dimensional space, this S times A. Okay? And now after I've projected them onto this space, now I find the best rank k approximation in this much lower dimensional space. Okay, using the coordinates representation of that space. Okay, now it's efficient, right? Because we said the SVD took number of points times dimension squared time. We still have n points, but they all live in a k over epsilon dimensional space. So now this is, you know, n times poly k over epsilon. Okay, and just like before, there are many options for choosing this random matrix S. You can choose it to be a matrix of IID normal random variables, but then computing S times A is slow. You can use a fast Johnson-Lindenstrauss transform, again with k over epsilon rows. It's optimal in the matrix dimensions, but to get n and z of A time, you can use count sketch matrix with a slightly larger number of rows. Instead of k over epsilon, it's roughly k over epsilon squared. It's k squared plus k over epsilon squared. Yeah, so this is the count sketch matrix again. You get n and z of A time. And all of these work in the sense that what you can provably show is that S times A contains a good k-dimensional space inside of its row span. Okay, I won't prove that here. But so therefore, if I project all the points onto that space and find the best rank k-dimensional space in there, then I'll get a 1 plus epsilon approximation. Okay, so now there is a caveat in the way I've described it so far. What is the current algorithm? We compute S times A, so we can do that very efficiently using count sketch, say n and z of A time. Then we project each of the rows of A onto S times A. Okay, so it's not so clear how to do that very quickly. Can we do that in input sparsity time? How slow is that? I'll get back to that in a second. And finally, we said once the points are inside of S times A, we can now quickly find the best rank k subspace just by using the SVD. So the bottleneck really is step 2, where we have to project these points onto S times A. But what have we seen earlier in this talk? What's one way of computing a projection? Any thoughts? So projection is just least squares regression. right? We said this earlier. So instead of computing this projection, why don't we just approximate the projection using our fast algorithms now that we have for least squares regression? Okay, so yeah, we can use the algorithms we described earlier. So basically, what does it mean to project the n rows of A onto the row span of S times A? It means to take each row of A and find the closest point inside of S times A in squared Euclidean distance. Okay, that means finding the coordinates of the first row of X, which determine the vector in the span of S times A. And I'm minimizing, I want to compute all the projections, so I want to take the sum over all the n rows and minimize that. Okay, so basically, if I solve this problem exactly, I would just be projecting the points onto S times A, but instead I'm just going to solve it approximately. Okay, so this is kind of like the regression problem we saw earlier. The only difference is, so it's transpose. The variables are over here now. And we don't have just a single B vector. The B vectors, we have sort of one for each of the rows of A. But you can still use sketching just as before. And you can solve this problem in n and z of A plus n plus d poly k over epsilon time. Okay, there's additional sketching. You just sketch on the right by a new sketching matrix R. And this allows for the whole procedure to be done up to relative error. And you get relative error for the low rank problem. Okay, so that's all I wanted to say about sort of the standard low rank approximation. Yeah?
Before we talk about relative error approximation, do you succeed with that, or do you need like an approximate solution? You use bound on the X prime, or distance between your X and the sketch.
No, so basically, no, we just need a bound on the cost. So yeah, so if you solve this problem up to 1 plus epsilon relative error, then you solve the low rank problem up to 1 plus epsilon squared relative error, which is still 1 plus epsilon. Yeah. So I didn't give the proofs for this, but you just need a bound on the cost. You don't need X to be close to the actual X. Yeah. Yeah. So the cost is the proof guarantees that the row span S times A contains a good solution inside of its span. Okay, and now we have all these points, and they have to go to this space. So you project them onto it, and then you find the best rank K space inside that span. And that procedure of first projecting and then finding the best thing inside the span, that's still optimal because of the Pythagorean theorem. I mean, I have to go there anyway, and then I find the best thing inside of there. So, okay. So let me just very quickly mention robust versions of low rank approximation. Just like for least squares regression, the SVD is sensitive to outliers since we're finding a space, a low dimensional space, which minimizes the sum of squares of distances to it. Okay? And so what you might imagine is just the natural, more robust version, like L1 regression, is to find a low dimensional space, a k-dimensional space V, which minimizes the sum of pth powers of distances for p less than 2. Okay? In fact, for p equals 1, this could be thought of as being even more natural than the SVD. Finding a low dimensional space to minimize the sum of distances to it. This is well studied. Yeah, so one nice thing about this is the cost is rotationally invariant. So I rotate the whole space. These distances are all Euclidean, so they're all preserved. And as I said, for p less than 2, it's more robust than the SVD. Okay, so what is known about this? So let me just formally define the notion of approximation. A k-dimensional space V prime is a 1 plus epsilon approximation if the sum of pth powers of distances to V prime is at most 1 plus epsilon times the sum of pth powers of distances to the best rank k-dimensional space. Okay, the same relative error kind of guarantee. And what was known is for any p, you can find a 1 plus epsilon approximation in n times d times poly k over epsilon plus a sort of hideous exponential and poly k over epsilon term, which I'll discuss more in a second. If you don't like this large term here, then you can instead relax the problem to output what's known as a weak core set. And all that is instead of outputting a k-dimensional space, I output a slightly larger dimensional space, a poly k over epsilon dimensional space. And the promise is inside of its span, there is a good k-dimensional space. It's just we don't know how to find it. And that's exactly where this hideous term is coming from. It's coming from basically enumerating over a large finite number of k-dimensional spaces inside of there. So if you allow for that, then you just get nd poly k over epsilon time. There was no hardness known for p less than 2, this robust case that I'm talking about. Though for p greater than 2, the problem was known to be NP hard to approximate up to a fixed constant factor. And there are algorithms nearly matching that approximation factor in polynomial time. So our results, so we show first, so for p less than 2, we get an algorithm running in time leading order term n and z of a. Okay, so instead of nd poly k over epsilon, we get n and z of a time plus n plus d poly k over epsilon plus this hideous term is still there. If you don't like this hideous term, then just like in previous work, we can remove it if you relax the problem to allow outputting a weak core set. And finally, we show actually that this term, some kind of term like this is necessary because we showed the first NP hardness for p less than 2. Namely, there cannot be an algorithm which is polynomial in all of the parameters. Okay. And this construction is, yeah, it's quite different than p greater than 2. It's like a different, a reduction from a different problem. And just like for regression, you can generalize low-rank approximation to many other cost measures, right? So y takes sum of pth powers of distances. I can find the k-dimensional space which minimizes the sum of m functions, the m function of the distances. And this, has, they're nice loss functions like the Huber loss function. And so we give the first algorithms, input sparsity time algorithms for this loss function, for this family of loss functions. So just to conclude, so I view sketching as a form of sort of homomorphic compression. So small sketches, they're nice. They sort of can match information theoretic bounds. They give rise to low communication protocols, etc. But oftentimes you want compression that is also useful. And if you have these kinds of sketches, what it is you take some problem, you sketch it to something smaller, and you can actually just solve the same problem on that sketch. Okay, so it preserves things like convexity, etc. So we saw sketching that it's useful for regression, low-rank approximation, and robust variance. Things that I did not talk about are it's useful for things like CUR decompositions, where you have a matrix and you don't want to just find an arbitrary low-rank factorization of it. You want to factor it in terms of a small subset of its columns and rows. It's useful for kernel versions of these problems, distributed computation inside of routines for linear programming, etc. And if you're interested in this, there's a recent monograph with sketching as a tool for numerical linear algebra, which has a lot of the proofs that I didn't discuss. So that's all. Thanks.